In the last lecture, we were doing the forced convection past a spherical particle. Okay, the forced convection past a spherical particle. A spherical particle with temperature T naught in a fluid with temperature T infinity far from the particle. Okay. In the limit of high Peclet number, where the free stream velocity times the diameter divided by the diffusion coefficient is large. Okay. In this limit, you would expect the disturbance to the temperature field to be restricted to a thin region near the surface. We had used the radius for scaling all length coordinates, okay, and we had used the free stream velocity for scaling the velocity. Okay. Substituted that into the equation. We were given expressions for the velocities in the radial and the axial direction. In this case, the radial direction is distance from the center, and the azimuthal direction is the angle theta is calculated with respect to the x axis, which is opposite to the direction of flow. And these were the velocity components that were given to us for the velocity profile. We had made the substitution, okay, in the limit of high Peclet number. You expect the disturbance to the temperature field due to the particle to be restricted to a thin region near the surface. That thickness of that region delta will decrease as the Peclet number increases in such a way that the convection and diffusion, the cross stream diffusion and convection continue to be of the same magnitude in this region. Okay. So, that is the rationale for choosing this boundary layer thickness delta. Okay. In this case, it is a scaled boundary layer thickness because I have defined a scaled coordinate. So, therefore, I defined the radius r star. Okay. I defined the radius r star. R star is equal to 1 is the surface. R star is equal to 1 plus eta delta is a small distance into the fluid, a small distance from the surface into the fluid. Eta is the similarity variable. Okay. Eta is the similarity variable which is order 1 throughout the calculation. Okay. Eta is the similarity variable that is order 1 throughout the calculation. Delta is the boundary layer thickness that goes to 0 in the limit as the Peclet number becomes large. We had used an expansion in small delta eta to calculate approximations for the two velocity components, okay. For the radial and the azimuthal velocity components, we had used approximations for small delta eta in the limit as delta eta goes to 0. Okay. We found that the radial velocity was proportional to delta square. The radial velocity was proportional to delta square, while the axial velocity was proportional to delta itself. And we had also found that the diffusion cross stream diffusion term, okay, the cross stream diffusion term for the diffusion from a spherical particle was identical to what we got from diffusion from a flat surface. And that is because if the radius of curvature is much larger than the boundary layer thickness, if the radius of curvature is much larger than the boundary layer thickness, the diffusion is effectively the diffusion near a flat surface. Okay. And so, the derivatives with respect to r, theta were all expressed in terms of delta and the boundary layer thickness eta, and this was the final expression that we got. Okay. This was the final expression that we got. Okay. A similarity solution can be obtained only if this term is a constant. Okay. A similarity solution can be obtained only if this term is a constant. As I told you, it can be any constant. Okay. In the limit as Peclet number goes to infinity, this has to be a constant value. It can be any constant value. The solution for T star in terms of eta will depend on the constant. The solution for the boundary layer thickness will depend on the constant, but the solution for T star in terms of the original variables, in this case r star and theta, will not depend on the constant. Therefore, we can consider this constant equal to 1 without any loss of generality. Okay. And then the equation for eta turns out to be minus eta square dt star by d eta is equal to d square t star by d eta square. That is the solution for the temperature field in terms of eta if this constant is equal to 1. Solution, this is the same as what we saw for a flat plate and for a stagnation point flow. Okay, this is same what we saw for a flat plate and for a stagnation point flow. Boundary conditions are the same. T star is equal to 1 at eta is equal to 0, the surface. T star goes to 0 as eta goes to infinity, okay, far from the particle. Okay. Equation is the same, boundary conditions are the same. Therefore, I can write T star, the solution is also the same, 1 minus 3 power 2 by 3 by gamma of 1/3 integral 0 to eta d eta prime e power minus eta prime cubed by 3. Okay. So, therefore, that is the solution for the temperature field. Okay. Now, we have to solve for the boundary layer thickness as a function of the streamwise coordinate theta. That equation differs from the flat plate and the stagnation point flow. Okay. So, the equation for this is 3 p by 4 into delta cubed cos theta plus sin theta delta square d delta by d theta. Deltas should all have stars because they are scaled. This is equal to 1. Okay, this is equal to 1. A first order differential equation for delta in terms of theta. Okay. Delta squared times d delta by d theta is equal to 1/3 of d delta cubed by d theta. Okay. Delta squared d delta by d theta is 1/3 of d delta cubed by d theta. Okay. So, this I can write it as sin theta by 3 d delta cubed by d theta. And this is a first order differential equation. Okay. I can reduce it to the standard form that where we can use the integrating factor. Okay. So, what I have to do is to multiply throughout by 4 by 3 PE. So, I will take on the right side I will have 4 by 3 PE. Okay. Okay. And then I multiply by 3 by sin theta. Okay. Okay. So, therefore, I will get d delta cubed by d theta plus 3 delta cubed cos theta by sin theta is equal to 4 by PE sin theta. Okay. Now, this is a first order inhomogeneous differential equation, first order linear inhomogeneous differential equation. Therefore, this can be integrated using an integrating factor. Okay. The integrating factor is equal to, so if I call this as this is of the form of the familiar form dy by dx plus p of x into y is equal to q of x. Okay. The integrating factor is equal to e power integral p dx, okay, is equal to e power integral d theta into 3 cos theta by sin theta. Okay, so, that is the integrating factor, which is basically e power integral the integral of this is log of cos theta. Okay. Sorry, log of sin theta. Okay. E power 3 log of sin theta is equal to log of 3 log sin theta sin of log sin theta log of sin theta cubed. Okay. So, e power log of sin theta cubed, which is a sin cubed theta. That is the integrating factor. Okay. Therefore, delta cubed can be written as delta cubed is equal to some constant by sin cubed theta plus 1 by sin cubed theta integral 0 to theta d theta prime times q, which is 4 by p sin theta into sin cubed theta prime. In the integral, it should all be theta prime. Okay. Okay. Which will be c by sin cubed theta plus 1 by sin cubed theta integral 0 to theta d theta prime into 4 by p e sin squared theta. Sin square theta is basically half of 1 minus cos 2 theta. Okay. Okay, so, this can be written as of 1 minus cos of 2 theta. Okay, which will be equal to c by sin cubed theta plus 1 over sin cubed theta into 4 by the Peclet number into theta minus sin of half theta minus sin of 2 theta by 2. This is delta cubed. Okay. This is delta cubed. Okay. So, obviously, delta is going to be 1/3, the 1/3 power of this. Note that it is proportional to 1 over sin cubed theta. Okay. So, therefore, this boundary layer thickness appears to be diverging at both theta is equal to 0 and theta is equal to pi. Okay. Theta is equal to 0, recall, is what is called the upstream stagnation point. Okay. And theta is equal to pi is the downstream stagnation point. Okay, theta is equal to pi is the downstream stagnation point. At the upstream stagnation point, the flow is incident on the sphere. Okay, as I told you in the last couple of lectures, the flow near the upstream stagnation point resembles that the stagnation point flow very close to the surface. Okay. At the upstream stagnation point, diffusion is outwards in the radial direction, convection is towards the sphere. Therefore, at the upstream stagnation point, you would expect the boundary layer thickness to be finite at the upstream stagnation point at theta is equal to 0. Okay. Therefore, we have to choose the constant in such a way that the boundary layer thickness is finite at the upstream stagnation point where the flow is incident on the sphere. Therefore, we have to choose the constant c equal to 0. Okay. The second term is 2 theta minus sin 2 theta. Okay. Near theta is equal to 0, I can expand this as 2 theta minus 1 2 theta minus 2 theta the whole cubed by 3 factorial, okay, plus etcetera. Okay. Sin x is x minus x cubed by 3 factorial plus x power 5 by 5 factorial plus etcetera. Okay. So, this the numerator 2 theta minus sin 2 theta is approximately equal to 2 theta the whole cubed by 3 factorial. Okay. That is the approximate value 2 theta whole cubed by 3 factorial. I have a sin cube theta in the denominator. Sin cube theta also goes as theta cubed in the limit as theta goes to 0. Okay. Therefore, the second term here is finite, okay, in the limit as theta goes to 0. Okay. So, therefore, I have to choose the constant c such that the boundary layer thickness is finite, that is c has to be equal to 0, otherwise the first term will diverge. Okay. Therefore, I get expression for the boundary layer thickness delta star cubed is equal to 2 theta minus sine of 2 theta by P e into sine cube theta, okay, or the boundary layer thickness delta is this whole thing to the 1/3 power. Okay. So, that is the expression for the boundary layer thickness. Okay. So, this is equal to 2 theta minus sine of 2 theta to the 1/3 power, right, by P e power 1/3 sine theta. Okay. This is finite in the limit as theta goes to 0 at this upstream stagnation point, as I told you. Okay. At this upstream stagnation point, this boundary layer thickness is finite, okay, in the limit as theta goes to 0. However, in the limit as theta goes to pi, I have 2 theta, that is 2 pi divided by sin theta, that goes to infinity. Okay. Okay. Therefore, the boundary layer thickness goes to infinity at the downstream stagnation point. Okay. Okay. And at the downstream stagnation point, you have a region which is called the wake. Okay. If you constrain the boundary layer thickness to be finite at the upstream stagnation point, as it should be, because flow is incident, the heat conduction is radially outward, and therefore, you would expect a finite boundary layer there. In that case, at the downstream stagnation point, diffusion is away from the surface, flow is also away from the surface, and therefore, the boundary layer thickness effectively continues till infinity. Okay. The boundary layer thickness is effectively infinite, right, okay, at this downstream stagnation point. That does not, however, affect our calculation of the flux. Okay. If you really wanted to find out the temperature field in the wake, then you would have to do an asymptotic analysis for theta close to pi, okay, and examine once again the balance between convection and diffusion. What is the thin region within which convection and diffusion are of equal magnitude downstream of the sphere. Okay. That is, however, not required to get the heat flux. Okay. I should also note that this wake is a temperature wake. It is different from the wake generated in fluid flows. Okay. So, that is a different phenomenon. This boundary layer separation and wake downstream of flows in the flow past a sphere. Okay. So, this is for the temperature field. The velocity field is still a laminar flow. Okay. In the viscous limit, the velocity field is still a laminar flow. This wake is for the temperature field. Okay. Okay. So, therefore, I have got an expression for the boundary layer thickness, which is finite at the upstream stagnation point, goes to infinity at the downstream stagnation point, theta is equal to pi. And I have an equation for the temperature field. Okay. So, therefore, the flux q r, okay, at r equals to r is equal to minus k into partial t star partial t by partial r at r is equal to r, which is same as minus k into T naught minus T infinity by R into delta star into dt star by d eta. Surface of the sphere is eta equal to 0. Okay, surface of the sphere is r star is 1 or eta equal to 0. Okay. And that dt star by d eta we have already calculated it using this expression here. You recall that the solution is identical for T star in terms of eta for all the problems that we have done so far: flow past a flat plate, stagnation point flow, pipe flow, and this flow past a sphere. Okay. So, this is equal to minus k into T naught minus T infinity by R delta into, if you recall, this was minus 3 power 2 by 3 by gamma of 1/3. Okay. This was just a constant value. Okay. Okay. Okay, so, this is equal to k into T naught minus by R into 3 power 2 by 3 by gamma of 1/3 and this delta. Okay. Note that delta is a function of theta. Okay. So, the flux varies as theta changes. Okay. Since delta is a function of theta, there is a variation in the flux as you go downstream. The average flux 1 over the surface area. Okay, by r square. Okay. Integral, okay, 0 to 2 pi of r square into d phi, integral 0 to pi of sin theta d theta times q r at r is equal to r. That is the average flux divided by the surface area times the integral over the surface of the flux. Okay. Integral over phi is just 2 pi, okay, and that r square cancels out. So, I will just get 1 by 2 integral 0 to pi, okay, sin theta d theta into q r at r is equal to r, that is k into T naught minus T infinity by r delta star 3 power 2 by 3 by gamma of 1/3. Okay. In this expression, the only thing that depends upon theta is the boundary layer thickness delta. Okay. So, everything else can be taken out as a constant. Okay. So, this is equal to k into T naught minus T infinity into 3 power 2 by 3 by 2 r gamma of 1/3 integral 0 to pi sin theta d theta into 2 theta minus sin 2 theta divided by whole power 1/3 by Peclet number power 1/3 into sin theta. I am sorry, I have written it the other way around. The boundary layer thickness, this should be 1 over delta. What I wrote was the boundary layer thickness delta. So, that 1 over delta will be of the form P e power 1/3 sin theta by 2 theta minus sin of 2 theta. Okay. And this integral can be calculated. Okay. This integral can be calculated. I will not go through the details of the algebra. All I will say is that Peclet number power 1/3 can be taken out. Okay. T naught minus T infinity 3 power 2 by 3 into Peclet power 1/3 divided by 2 r gamma of 1 by 3 integral 0 to pi sin d theta into sine square theta by 2 theta minus sine 2 theta. Okay. And sine square theta is half of 1 minus cos of 2 theta. Okay. So, you can see the derivative of the denominator is the numerator. Okay. The derivative of the denominator is the numerator, okay. And I have to have a 1/3 here. Okay. The numerator is the 1/3. Okay. The numerator to the power 1/3, okay, this 2 theta minus sine 2 theta power 1/3, the derivative of that theta 2 theta minus sine 2 theta is the numerator to within a factor of 2. Okay. So, using that you can do the integration, okay, and ultimately what you get is 3 power 5 by 3 pi power 2 by 3 k into T naught minus T infinity P e power 1/3 by 2 power 10 by 3 gamma of 1/3 into r. Okay. This is effectively 0.496 k T naught minus T infinity e power 1 by 3 divided by r. Okay. So, this is the average flux. Nusselt number is equal to q average by k into T naught minus T infinity, usually scaled by the particle diameter, not the radius. Okay. And this gives you effectively 0.992 P e power 1/3. So, this is the solution for the Nusselt number correlation for the flow around a particle, laminar flow in the low Reynolds number limit, but high Peclet number limit, okay, the limit of high Peclet number and low Reynolds number, because the velocity profile that we had used is valid only in the limit of low Reynolds number, where there is symmetry between the upstream and the downstream directions. Okay. One curious fact that you would have noticed is that the expression for the temperature field in terms of eta turned out to be the same independent of configuration. Why is that, and can we get a solution for a general flow field which is independent of configuration? Okay. For a general flow field where we just specify the velocities close to the surface, can we get a solution for the boundary layer thickness and the Peclet number? Okay. So, that solution for a general flow field I will consider in the next lecture. I will just consider a case where velocity varies as a function of x and z, where x is the streamwise coordinate, z is the cross stream coordinate. For that velocity variation, I will try to derive the expression for the boundary layer thickness for a particular variation of the velocity in the streamwise direction. Once you have that boundary layer thickness, you can substitute any variation that you want and get the boundary layer thickness, and then integrate over that boundary layer thickness in order to get the solution for the temperature or concentration field. So, this problem of a general flow field for the flow past a surface with a no slip condition at the surface, I will continue in the next lecture. Okay. I will see you then.